A couple of months ago, I decided to build my own real-time operating system. You see, I recently moved across the country and had to leave a lot of my electronics behind. But as I got more interested in the world of embedded engineering, I realized that I needed the hardware that I left over 2,000 miles away. So there I was, with the goal of creating an operating system for hardware, with no actual hardware. But I wasn't going to give up on my goals just like that. I needed a way to dive deep into the world of operating systems, which is why I created my own real-time operating system emulator called Tuscan. You see, this was going to be a project that only took a couple of weeks until my new microcontroller would arrive, but almost 2 months later, here I am still working on it. This video is the beginning of a multi-part series where I take you through the creation of my real-time operating system, including all the successes and failures. I hope you're able to learn something, and maybe even build an operating system of your own by the end of the series. So let's start at the beginning, shall we? First, what even is a real-time operating system? In general, operating systems manage a computer's resources, like its compute or memory, for the user and the applications. Most operating systems you've heard of, like Windows or Linux, are meant to maximize how much of the system is utilized. These are called time-sharing operating systems, but they're a little bit different than real-time operating systems. You've probably seen the Wheel of Death or had your computer freeze up on you at some point. This is because the operating system is managing so many different resources at once that it puts your task on hold while it goes on to handle other things. In a time-sharing operating system, there are no strict requirements for when the task is completed. This might be allowed for situations where the user can just wait for the operating system to get back to your task, but imagine if this happened on a critical piece of hardware, like a pacemaker or a flight controller for a rocket. In cases like these, real-time operating systems, or RTOSs, are used. In RTOS, it guarantees the execution of a task within a strict deadline, making the response time of each task very predictable. RTOSs are also typically smaller in size than a time-sharing operating system. It's incredibly popular in the embedded world because the hardware is typically more limited in memory and storage, and the use cases are for more time-sensitive tasks. Now that we know what an RTOS is, what goes into making one? Because we're making an emulated RTOS, we can simplify a lot of what goes into it compared to a regular RTOS. For our RTOS, it can be roughly categorized into 5 main components: tasks, the scheduler, intertask communication, interrupt handling, and a timer. The timer is pretty simple. It's a pulsing clock, like a heartbeat, that all other parts of the operating system use to keep track of how much time has passed. But the other 4 components can be pretty complex, so let's break down each of them one by one. Tasks can be thought of as small independent programs that can be executed depending on the context. For example, reading data from an I/O port can be considered one task, while blinking an LED might be considered another task. The scheduler is the control tower of the operating system. It controls how to allocate resources to the different tasks by scheduling them to execute at a specific time. The way the scheduler chooses the task is called a scheduling algorithm. Some of the most popular scheduling algorithms include round robin, priority, first come first serve, and multi-level feedback queue. Intertask communication is how different tasks can communicate data with each other. Say, for example, I read in data from a proximity sensor and I want an LED to turn on if it senses something close to it. In the context of an operating system, we can create a task to read in the data of the proximity sensor and another to control turning the LED on and off. But to know when to turn the LED on and off, it needs data from a different task. Since tasks are independent of each other, inter-task communication is needed to share data between the tasks. As mentioned before, real-time operating systems guarantee that a task is completed within a certain amount of time. So if a task comes in that needs to be executed immediately, it uses interrupts, which is handled by something called the interrupt service routine, or ISR for short. Oh, and here's where I should probably mention that I'll be using C++ to code everything, and I'll only be using the standard library. This is the first video in this series, meant to teach you about the core building blocks of our real-time operating system. In the next video, we'll start by writing our very first lines of code for this project and get a working task class going. Make sure to subscribe so you don't miss it.